Good morning friends, welcome back to Panika Tutorials. In this video, I want to discuss two more numerical questions related to paging. These kind of questions will help you to understand the concept in a better way. So I request everyone to watch the complete video for better understanding. First let me read out the question number 1, then I will discuss the solution with you. Look at the question number 1. Virtual address space is 8 MB, page size is 8 KB. Find the page table entry size such a way that page table will fit in one frame of main memory. Okay, if you look at the question carefully, they have given the logical address space. The logical address space is the process size. Each process is logically divided into pages. Okay, you will have page number 0, page number 1, page number 2, so on. And the main memory is logically divided into frames. Okay, and remember one important point, frame size will be equal to page size. Whenever CPU is executing a particular process on demand, the pages will be stored in the main memory. Suppose let's take that page number 1 is loaded in the frame number 2. Similarly, page number 10 is stored in frame number 3. Now, this information somewhere we need to maintain. So, that information will be maintained in a page table. So, each process will maintain its own page table. Now, you will ask me, sir, how can we find the page table size? The page table size depends on number of entries and the size of each entry. Now, the number of entries will depend on number of pages. Suppose let's take that you have 16 pages in a process, then you will have 16 entries. And each entry will store the information. Suppose let's take that it is page number 0, page number 1, page number 2. Okay, now currently page number 1 and page number 10 is stored. So page number 0 is not stored in the main memory. So page number 1 is stored in the frame number 2. Similarly, page number 10 is stored in the frame number 3. So it will have each entry will have the information such as frame number, in which frame of the main memory it is stored, and also present or absent bit, meaning is that the particular page is stored in the main memory or not. Look at here, page number 0 is currently not there in the main memory. So the present or absent bit will consist of 0. Meaning is that the particular page is not there in the main memory. If it is there, we will have the information called 1 here. Similarly, we will have cache enabled, disabled bit, protection bits we will have, dirty bit we will have, reference bit will we have. So all this information will be stored in one of the entry in the page table. So now what they are asking, find the page table entry size they are asking. So this size we need to find. And what they are telling, such a way that page table will fit in one frame of the main memory. Usually, the page table will be stored in main memory in one frame. If the page table size is more than frame size, then we will go for the multi-level paging. Is it clear? Now what they are telling, if it should fit in one frame, so we should go for single level paging. And now we need to find the page table entry size. Is it clear? To do that one, first I need to find the number of entries in the page table. The number of entries in the page table will depend on number of pages in a process. So first I need to find the number of pages. So how can we find the number of pages? Number of pages is equal to process size or logical address space by page size. The logical address space is the virtual address space, which is 8 MB, and page size is 8 KB. So bytes and bytes will be cancelled, 8 and 8 will be cancelled, so you have 1K pages will be there in the process. If you have 1K pages, then page table will have 1K entries. So number of entries in a page table will be 1K. Okay, they are asking the page table entry size. Entry size they are asking, and they are telling that it should be fit in one of the frame of main memory. So we should know the frame size. Does anywhere they have given the frame size? They have given the page size. So if they have given the page size will be equal to frame size. So frame size is 8 KB. Okay. Now with this information, we have to find the entry size. So number of entries into entry size is equal to page table size. Now what they are telling, it should fit in one of the frames. So max it will be frame size. Okay, what is the frame size? Frame size is 8 KB. So number of entries are 1K entries are there, and the entry size you need to compute. Let me keep it as yes. Is at least means not at least, is less than or equal to 8 KB, means at most you can have. So then S will be less than or equal to 8 KB by 1K. So K and K will be cancelled. So you will have 8 bytes. So page table entry size at max it will be 8 bytes. If it is less than 8 or equal to 8, it is not a problem. If it is greater than 8 bytes, then page table cannot fit in one of the frame. So this is the right answer for this question number 1. Now look at the question number 2. They have given the virtual address space which is 512 MB. Page table entry size they have given as 4 bytes. Now they are asking the page size. Leave about this page size. They are asking us the compute the page size with this information. Okay, so to do that one, let me use the concept. So remember one thing, again we have to find the page size such a way that page table will fit in one frame of main memory. Because the space issue again I have not written, they have given the virtual address space, page table entry size they have given. Find the page size such a way that page table will fit in one frame of main memory. So we need to find the number of entries in the page table. Number of entries in the page table will be equal to number of pages. Number of pages is equal to logical address space by page size. Okay, logical address space is 512 MB. Okay, by page size we don't know, we will assume it as P. So 512 MB is nothing but 2 power 29 bytes by page in bytes. So bytes and bytes if you cancel, the number of pages will be 2 power 29 by P. Is it clear? These many pages are there. If you have these many pages in a page table, you will have 2 power 29 by P entries will be there, because in a page table the number of entries will be equal to number of pages in a process, and they have given the entry size as 4 bytes. Okay, and they are telling that the page table will fit in one frame. Fit in one frame means it should be equal to page table size. Okay, but they are telling it should fit in one frame of main memory. So one frame means frame size, but they have not given the page size, they have not given the frame size. So page size will be equal to frame size. So I will consider it as P only. Are you able to understand? Because they are asking us to compute the page size. We have assumed the page size as P. Page size will be equal to frame size. So this will be equal to P. It should be less than or equal to P, because at max the page table size should fit in one of the frame. So now with this information, let me compute this thing. 2 power 29 into 4 bytes. Okay, which will be how much? 2 power 31. Are you able to understand? If we keep 31, it will not fit anywhere. Let me keep it here. Will be equal, less than or equal to P square. 31 will not be exactly divided by 2. So what I will do, consider it is, instead of 4 bytes, I will consider it as 8 bytes. Okay, are you able to understand? So 2 power 29 into 8 will be 2 power 32. Is it clear? 2 power 32 is less than or equal to P square. Then P square is greater than or equal to 2 power 32, which will be equal to P will be greater than or equal to 2 power 16. So page size is at least should be 2 power 16. Are you able to understand it or not? If this page size is this much, then page table entry is this much, then we can fit a page table in one of the frame of main memory. I hope you have understood this concept. If you still have any doubts related to these two numerical questions, feel free to ask me in the comment section. I will try to clear your doubts as early as possible. Thank you for watching the complete video. Have a nice day.